Welcome, engineers. My name is Travis IQ, and today we're talking network address translation. Not necessarily a security principle, although some people think that it is. But let's get into it. Network address translation. We need to give you a little bit of information about what it is and some context as to why we do the things that we do, right? And so the first thing we need to do is get me set up here in our virtual studio, as it were. So the first thing that we need to understand is we'll talk about network address translation, but why this is weird. And if you've heard me talk here on this channel before, you've heard me say that routers route traffic, and routers don't do anything with the packet itself. So a packet comes in to an interface, and the router says, where does this thing go? And the router then forwards it on to the next hop router of which it needs to go to. Okay, so if we have this fundamental understanding of routers, routers are like USPS mail carriers. They look at the outside and they go, yep, this is where it's going. And I tell you all the time, I say this in my live classes as well, that routers don't actually do anything with that packet information. They look at the source and destination and forward traffic this way. So why do we need to know this? Why did I even review this? Because network address translation actually changes the function, network address translation. I'm going to call this NAT from now on. NAT actually changes part of the functionality of this router or firewall or intermediate utility, whatever is doing it. We'll say it routers in this case, but it could be different devices. But it could be your edge router, which also acts as a firewall and does other things. But let's just say it's just your router. So R1, it actually changes the functionality of R1. And what R1 does now is R1 actually translates the network address. What is the network address? The network address is the IP address. Specifically, in the case of edge routers, it translates the source IP address of this host. So if we have host 1 out here, host 1 is forwarding this packet into R1, and what it actually does is it translates the source IP address to a new source IP when this thing pops out on the other side. We're going to give a little bit more information about this as to how it keeps a table of information and knows which address to translate to which when it comes in and goes out and these types of things. But that's what network address translation is functionally. It translates an IP address, changes it in the header, and forwards it on. So that's what makes it weird. What makes it useful? So where did network address translation come from? Where did NAT come from originally? So there are a few different reasons and utilities for it, but the primary use case in terms of its initial introduction was we were running out of IP addresses, and address translation allowed us to conserve IP address space. This is one of the primary functionalities, right? It allowed us to NAT conserved IP address space. Specifically, IPv4 address space. So this is your traditional 32-bit address, and we were running out of addresses. Currently, we have, in fact, run out of addresses. We could talk about what that means contextually in terms of the regional registries and IANA and things like this, but we're not going to get into that in this video. What it means is we were running out of IPv4 addresses, and what they said is, well, what if I had my edge router here, R1, and I had my internal LAN, my local area network, and I had the WAN, the wide area network, the world, and these all require global IP addresses. And so out here in the world, you need a global IP address. You need a unique address that identifies you in the world. We've talked about this, your street address. Well, does every host inside this LAN need a global IP address? And the answer is no. Every host in here can communicate internally with one another via a private IP address space. Let's think about something like 192.168.1.0/24, this address space that you could be familiar with in your home or small office environments. And then when I leave this address space, this is a private address space. I think we've talked about these on this channel before too. This private address space is not globally routable. Routers in the internet, WAN routers, will not route source or destination IP addresses, destination IPs of private address spaces. They say this is no good, right? And you might have heard the term bogon before, bogus addresses. as these are examples of those address spaces. The 127 address space is another example of that. And so we use this private address space for all of my internal hosts to communicate. I would say it's similar to like your first name, right? In here, in your home, you can use first names, or in a small office, you could use first names, but you would never go out and try and get to someone on the other side of the world by first name. It doesn't make any sense, right? You need a global address that you can get information to them for. Okay, so we have this internal address space, but it's not globally routable. We do this to conserve global addresses so that we don't have to address every single host internally this way. So then what happens? So I need a globally routable address. And so what my WAN does, my internet service provider, ISP, provides this interface with an IP address, or more than one IP addresses. Let's say multiple IP addresses so we can make this a little bit more simple. So I've got IP addresses here, globally addressable IP addresses. Global. And what this router does is this router translates 192.168.1.1 to 204.24.11.98. And so there's one host in here that needs to get out to the WAN, and that host, the .1 host, now has the address 204.24.11.98. And so now it has a globally addressable address, and all the other hosts in here do not. So we've conserved IP address space, but we've also given the host internally the opportunity to communicate globally because it does have a usable IP address. We just need to translate it at the router. So you could see where this also institutes some problems, where we have like a one-to-one translation like this. If I don't have enough IP addresses externally for internal hosts, I could run out of IP addresses. You might say, well, Travis, I don't run out of IP addresses in my office. So then what's going on? There's a bunch of other peripheral technologies here, like port address translation, PAT, and NAT overloading, which is basically that equivalent term, but in the Cisco world, we use the term overload. So there are solutions to this, but I'm trying to give you the introductory content here for address translation. Then we'll talk about those solutions as we move forward. So that's what we do here at translating this address. What does it look like functionally in the router? So we need to go internal, right? So when we set this router up here, R1, what does network address translation look like when we have R1? We have the internal LAN, and we have the external WAN. And so what happens is H1 has an IP address, 192.168.1.101, and R1 has, first of all, R1 has an IP address here, right? That's the default gateway. So 192.168.1.1 is this address interface. And then this interface here is the globally facing interface. So it's been given an IP address from the ISP. And this is 204.4.14.81. And so when host 1 tries to communicate with an email server, mail.iq.com, I would write out intelligence quest here, but it's too long. When this host tries to communicate there, this is an IP address of 107.11.98.14. And if you're wondering what all the other header information looks like, the MAC address header, the MAC address information, right, the Ethernet header, the TCP header or UDP header in these cases, right? I do have an OSI model discussion, so we're not going to go into the other headers and what this full stack looks like. We're just discussing layer 3, the network layer here, because that's what R1 is manipulating. And there are other things going on, but this is the most important component of NAT for us. Or this is the only component that NAT addresses. Well, it could address TCP as well, but we'll talk about that. So what happens when H1 tries to communicate to mail.iq.com? We have a network header, and that header has a source IP address where it's coming from, 192.168.1.101, and a destination IP address, 107.11.98.14. And when this gets forwarded to R1, R1 knows darn well that this IP address is not routable, 192.168.1. The 192.168 space, that's a private address space. And so R1 has to translate this address, and we've told you that it is conducting address translation. And so what R1 has to have is what? A table of information to look it up. That's how all of your computing devices work. Your switches with MAC address tables, your routers with route tables. Now we've added an additional solution, address translation. So what do we have? It's a network address translation table, a NAT table. And so in this case, we have, this is the inside address, this is the inside interface, this is the outside interface. And so we have a table that says translate 192.168. This is a static translation. This is the most simple case. And so this is why we're introducing it, is because it's the most simple case. Translate 192.168.1.101. Translate that address to 204.4.14.81. And so what this does is it translates. So on this side, this is what the network header looks like. And when it comes out here, the network header looks like this. Source 204.4.14.81. Destination 107.11.98.14. And so when this gets forwarded on to the next router just looks at the destination IP and says, oh, 107.11.98.14. I know where that goes. And it forwards it on to the mail server. The mail server then, what does the mail server do? The mail server looks at the destination, says, oh yeah, that's me. We're good with this. It then looks at the additional information and processes the request, whatever it is, whether it's IMAP, MAPI, or some of these other email protocols, POP or something like this. It translates, it produces a response, and then it looks at the source and it says 204.4.14.81. That's where I need to send it back to. And so the back half of this is the mail server then responds. And what does the network header look like? The IP address, source and destination information look like? Looks like this. Source is now who? mail.iq.com, which is 107.11.98.14. And the destination is now 204.4.14.81. That's how we get back. 204.4.14.81. And so this gets forwarded on to this intermediate router. The intermediate router looks at 204.4.14.81, knows where it goes, and it sends it to R1. R1 sees this destination, 204.4.14.81. That's this, 204.4.14.81. And when R1 sees this IP address, it looks it up in its network address translation table because it goes, oh, I know this address. It says 204.4.14.81. I need to translate this address to 192.168.1.101 because that's what this router does with NAT configured. And so when this gets forwarded on, R1 translates this destination now, right? Because this is the outside interface, this is the inside interface. And so in this case, it's inside, it knows that the source is being translated. In this case, it's outside, it knows that I'm translating the destination now because that's the address that I would be looking at for translation based upon this nomenclature here. And you can see this nomenclature in the Cisco CLI. You'll see it in other CLIs as well, and you'll also see it in GUIs and things like this when you're working with routers in their user interface, their graphical user interfaces as well. The in-out nomenclature, because it needs to know which address it's looking at, and the reason that we use this terminology is to tell that router that specifically. Okay. So on this side now, what does the network header look like? This is what we're showing in these brackets. This is the network header. So on this side, the network header has a source address of still 107.11.98.14 and a destination now of 192.168.1.101. And this gets forwarded on to host 1. And host 1 looks at the destination address and says, oh yes, that's me. And then it looks at the internal content, pop, IMAP, MAPI, some custom response or something like this, and it processes it. So this is network address translation in a nutshell. And if I were to ask you, for example, right, what the destination address of the packet is when it's forwarded from R1 to when it's forwarded out of the R1 interface, you could tell me this based upon the description that I've given you here. So this is the base function of network address translation, specifically a static network address translation. Now that we know what the functionality is and why we decided to do this, we can also talk about things like benefits and drawbacks. And so this is where it gets a little funky, where if you remember at the start of this discussion, I said, so let's do NAT benefits and drawbacks. And at the beginning, I said network address translation is not a security tenant. And so while there is a benefit in terms of, we would call this obfuscation of your internal network, that's not necessarily a security tenant. It's basically, right, you're obfuscating the internal addresses. And so there is some benefit in terms of the external world not knowing what your internal addressing scheme looks like, but it's not necessarily a security tenant because it doesn't necessarily prevent any communication. It's not a firewalling functionality. It's not a filtration functionality. None of those things. It's simply obfuscating, right? Hiding some of this internal information, which is somewhat of a benefit. There is also a benefit. We already talked about the initial benefit, which was conservation of address space. It's not necessarily a huge benefit now, but it was. And then finally, there's a really big benefit too, which is one of the reasons why this is going to stick around, which is consistency of internal addressing. If you're someone like me who does networking and cybersecurity consulting, right? Consistency of internal addressing, that actually helps me, right? It helps me because when I go into an environment and we're using the 192.168 space, we're using the 10, this is a /16, or we're using the 10/8, and you're using the the second octet to denote building or something like this, and the third octet to denote floor. You're helping me kind of understand, or you're giving me some information about what the addressing scheme looks like. I'm actually more familiar with this already, and if you're a network engineer and you're moving companies, or if you're a network engineer and you're setting up a new facility, then you're going to utilize this consistent internal nomenclature because that's what you're familiar with. It takes a load off your plate so that you can do other things, which is focus on the network itself and addressing schemes and routing and other things. So there is some benefit here to this entire infrastructure. Now you might say, now that we've transitioned to some extent to v6, that there is less benefit to address translation than there was previously, and I would agree. And there's a reason that ISPs and a lot of internet traffic is routed as v6 because there's some computational overhead that is saved using v6 headers and things like this. But we'll save that discussion for another day as well. Drawbacks. Drawbacks are, there could be a drawback in terms of obfuscating the internal network. I would say one of the primary drawbacks is lack of end-to-end connectivity, lack of end-to-end consistency. And so what this does is when you start translating addresses in the middle of that route, is what it does is it breaks down the end-to-end IP addressing consistency, so it breaks down specific functionalities, right? It makes it more difficult to facilitate effective VPN encapsulation. It makes it more difficult to troubleshoot. So this is, encapsulation becomes more difficult. Troubleshooting becomes more difficult. And as a result, because there's a difficulty in the analysis of that traffic to some extent, it could put into question some security, right? And so can you maintain consistency? Does that help? Does that hurt your security posture to some extent? Not understanding the end-to-end IP connectivity is what you usually see. You usually see it as IP connectivity, end-to-end connectivity. And so there are benefits and drawbacks. Obviously, it's used all over the place. This is part one of a multi-part series on address translation because we had to give you some context, we had to give you some base functionality, and we had to discuss some of the benefits and drawbacks. In the subsequent videos, we will talk about network address translation in the context of one address to multiple internal addresses or multiple addresses to multiple internal addresses. That would be dynamic network address translation. We'll talk about one address to multiple external. So that would be port address translation utilizing some additional identifier, or PAT, something that you've probably heard of and seen, and maybe you're asking yourself, I was hoping that you would get to that here. We will, but the videos get long. And then we'll talk a little bit more about, so we'll talk more about PAT. We'll also talk about another component known as port forwarding, which is another pretty cool topic. So this is all going to be within the context of this long discussion here. We'll put out a couple of videos. As is always the case, engineer, break stuff, have fun. We'll see you next time. We're going to keep going.